William Lindved talking about the electromagnetic horizon.
So I'll be talking about some work that I've been doing with Anton, we should all be familiar with by now. So essentially, the point of this is to understand QFT better in strong field backgrounds and ultimately make sense of double copy and how it might work in the presence of background rules. That's sort of the main aim. And for this reason, we've been trying to look at a certain class of electromagnetic backgrounds of strong fields, which have the benefit of being able to be studied analytically, and they already have some sort of phenomena that already exist in gravity, which makes them sort of a nice, possibly a nice toy model to the double copy in. So one of the main sort of reasons why we can study this system analytically is thanks to light coordinates. So we'll just very quickly review what they are. Take your time, your space, you make them into null coordinates instead. And then you have its other momenta, which electron momenta, and they're always positive. And then everything is going to work out nicely once we look at our system. So we have like our Penrose diagram here of empty Minkowski spacetime. And the idea is to put an electric field on it. I'm going to put this certain electromagnetic field on it where we turn it on at some light runtime. We turn it off at some other light runtime, and it's going to be a function of light runtime. And the one we're going to choose is this particular one, which turns out to just be an electric field, which is going in the same direction as the pulse, if you will. So we just have an electric field, which is longitudinally polarized. For the purpose of this talk, we're also just going to say that it has the same sign all the way, just to highlight the phenomena that we're interested in. We have this classical potential, which is just an integral of the electric field, which is going to be useful in a moment. So you can ask yourself, what's this field do? So classically, we'll start classically. So what's going to happen if I put an electron or a positron in the in region? So that's going to be accelerated by the field. And to begin with, we're just going to ignore radiation and self-force effects. We're just going to say that this is moving in the background, analogous to geodesic motion on a curved background. And then the equations of motion are just the Lorentz force in a fixed background. And this is easy enough to solve. We're just going to care about the plus and minus directions, because that's where all the dynamics happen. We can do it in the other ones too. They're just sort of along for the ride. And then we can solve the Lorentz force equations for the momenta, and we get these expressions here. The pi plus is sort of the the amount of an electron at some light runtime. We can instead have it as a function of proper time via this relation here for proper time, but then the equations get a lot more annoying to deal with. So what happens if I actually put an electron in the region? Like, what's it going to do? We solve with this as well, not too difficult. Most of the time it's going to start, it's going to be accelerated by the field, it's going to come out on the other side with some different momenta. So it's showing a velocity memory effect. It's going to come out with this different momenta, p plus minus b. But we can see also that there's a denominator in this expression which can go to 0 if the initial momenta is too small. And then the equations diverge at some critical time, which we're going to call, well, x minus c. And what happens then? So classically, still, this is not so difficult to understand. Really, these electrons get accelerated to, towards light speed, and they never come out into the out region. And even though they sort of disappear, they do everything they can do in a finite light runtime, but this still happens in infinite proper time. So it's sort of, we have an electron that gets accelerated towards light speed, faster and faster, and in this sense gets cut off from the out region, or this null surface at this critical light runtime. In this sense, it's sort of seeing an acceleration horizon there. This is very similar to the Rindler horizon, only we have sort of a variable acceleration rather than a constant acceleration in the Rindler case. So you might think this is a bit weird, and maybe we missed something in using sort of the geodesic idea. We can put radiation back in, using the Landau-Lifshitz equation instead. And then it turns out that this horizon is still there, and it's just actually moved to earlier times, so this effect is even stronger. We can also see what happens to positrons. So because we have an electric field that never changes sign, positrons are just accelerated in the other direction. And because of this, they can never get trapped in the field, which should be fairly clear on geometrical grounds here, because it's accelerated sort of in the opposite direction of that the pulse is moving. And then everything is nice and smooth. They come out in the out region with, again, showing a velocity memory effect. And it comes out of the field in the out region, crucially now, with a minimum momenta. So since the light momenta are always positive, the positrons in the out region always have a minimum momenta of B infinity. So just to summarize what happens classically. So if you have an electron in the in region, if it has a small enough momenta, it's going to get trapped by the electric field and then come out into the out region. The ones with larger momenta are going to get accelerated to and reach the out region, where they can have any momenta. And all of the positrons go through the field, but they come out with a minimum momentum. And that's sort of the summary of the classical. So now we also want to sort of understand what happens, when we add quantum to the equation. So we want to sort of understand what happens if I start with the system with an empty space-time. I turn on an electric field, I turn it off, and then I'm sitting in the out region and I'm looking at what does it spit out. So we would expect that there's pair creation in this field. It's been known that these kinds of fields produce pairs for a long time. Also, pair production has been studied in these kinds of field using various formalisms. So it's been studied using word line formalism and two-time formalism, various other formalisms. But we're going to try to get at it using more standard amplitudes method. And we're going to be able to compute correct observables this way, but we'll have to have some ambiguities which relate to this horizon that we just discussed. So the computational machinery we're going to be using has been extensively discussed by Anton in the lectures, which we'll have a wee review. So we're starting essentially from the background field QD Lagrangian. Since these external fields might be strong, we want to do perturbation theory in that. So you rearrange the Lagrangian into a free part, and it's free in the sense that it's quadratic in dynamical fields. And then we do perturbation theory in the dynamical photons. And this is called the Furry picture. When we're computing this in this picture, the difference is that the propagators become more complicated propagators. And if we have external states, then in the amplitude, they're going to show up as wave functions in the amplitude. We're also going to be using the perturbiner method to compute these things. And as we know from Anton's talks, 2-point amplitude, which is what we're interested in for pair creation, we're interested in the 0 to 2 amplitude, is a boundary term. The boundary for the specific system is these ones here, the green and the red ones. The green ones are going to just turn out to be 0 trivially, and the boundaries on the electric field are the ones that are going to be important. So in order to compute anything, we're going to need the wave functions. And these are just the solutions to the wave equation. So we're going to be talking about the scalar QD case, where the Klein-Gordon equations in background. Everything qualitatively transfers to spinor case as well. Exactly the same qualitative behavior is there as well. So the wave functions for incoming particles look like this when you solve the wave equation. You can see that the first exponential here is sort of just saying what's the momentum of these incoming particles at various light front time. Then we have the square root factor is just some normalization. And then we have an extra exponential, which can, in principle, be more interesting. And these wave functions sort of encode the classical kinematics as well. So if you have a positron that's going to come through the field, and if we look at what happens to that at large light front time in the out region, that's going to have this minimum momentum that we saw before from the classical case. And for electrons as well, for the ones with a large P plus, the same thing happens. But something again goes wrong when for these low energy or low P plus electrons, where we have a singularity in the integral that we'll need to make sense of. So classically, you just thought that this just gets accelerated to light speed, and that's fine. But quantum mechanically, we might expect that it could tunnel through or do something. So we're going to have to find some way to analytically continue this wave function. And one thing we can try is to just go around the pole and try to do the integral. This gives us a principal value integral, which is we can evaluate, and a funky factor to the right with a non-perturbative dependence on the electric field. Unfortunately, this doesn't describe an electron that's tunneled through the field, because it has no overlap with outgoing particles. So it doesn't describe an electron that's tunneled through the field. So because we have this extra exponential factor that appears just at the horizon, the wavefront doesn't have a preserved norm. And there's also many different choices of analytic continuation that would be fine, essentially because we can turn off, and at the horizon we can turn off and turn on any solutions that are solutions on either side of the horizon. And because there's sort of nothing to tell us which is the correct choice, we won't be able to uniquely identify an S matrix, which is not the greatest thing for unitarity. But to understand pair creation, we don't really need this. So let's look at the outgoing wave functions instead. And for this, we're going to define this A of x, which is very similar to B of x minus, only this vanishes at infinite light front time rather than in the in region. And the outgoing wave functions look very similar to the incoming ones, only now we have a singularity for positrons at another horizon, if you will, at a past horizon, which solves this P minus A is 0. So and this corresponds exactly to the positrons which wouldn't be in the out region classically. So these are the positrons with P plus is less than B infinity. So we're going to have to try to continue this wave function back across the horizon for this to cover the entire field. We can do this again and get, again, something similar. We pick up this extra exponential factor. And this extra factor looks a lot like a Schwinger factor. So it's a non-perturbative factor, which shows up a lot in pair creation, shows up in Schwinger's original paper of this effect. And in the out region, it definitely describes a single pole. So we interpret this because of this, that it's a positron that's been pair created by the field, which is now there. But we don't have any wave functions which describe positrons that have been pair created by the field. So where have the electrons gone? So that's sort of the thing that might be puzzling. So to understand this, we're going to look at some amplitudes. And again, I remind you that the sort of idea that we want to think of is we start with nothing in the in region, we turn on the field, we turn off the field, and we see what comes out. We can try to compute the probability of finding an electron-positron pair in the out region. And this is given by this boundary term where we have an outgoing electron wave function and an outgoing positron wave function. And we're evaluating on these, again, these boundaries. However, this is proportional to this delta function, and because light front momenta are always positive, this always gives 0 on all of the boundaries. So this is a bit weird because we know that there is pair production in the system, but well, this amplitude is 0. So we're missing something, and we're asking the wrong question for what pair production is in the system. So the correct question to ask is, what's the amplitude for finding only a positron in the out region? And that's also given by this term in our method amplitude, the surface term. We again have a delta function. However, this is now has this dependence on the electric field on it. And as we go past the horizon, this term P plus minus A changes sign. And now we have support for the delta function. And it instead sets sort of the maximum sum of these light front momenta, which means that we suddenly get a non-zero contribution on this red surface. We can move on with this and find the pair production probability. which agrees with the literature. We have it's a locally constant approximation, which is essentially Schwinger's original result, but for variable electric fields. And we have this, again, this Schwinger factor on the right, which has a non-perturbative dependence on the electric field. So we really couldn't have hoped to find this using perturbative methods. And this is the pair production probability that people have found using other methods. And this sort of shows that the probability of observing a pair created positron in the out region is equivalent to the probability that there has been pair creation. So we conclude from this that there has been pair creation. The two particles have been created, but only one of them reaches the out region. And the information about the created electron is in the analytic continued positron wave function, but the information about the electron is hidden behind the horizon. In the out region, it describes only the positron, and as we go behind the horizon, suddenly we have the information about the electron there. And it also sounds interestingly sort of like Hawking radiation, in the sense that we have on the horizon we have pair production. One of the particles ends up in the out region, and one of them stays on the other side of the horizon. Right, and the summary of this is that we found this strong field QED system where we're able to find some analytical results, and we managed to compute a lot of these, some observables, using standard amplitudes methods, finding analytical results that agree with the literature. And the system itself has a lot of phenomena that we have in gravity already, and these are mainly these horizons and Hawking radiation type phenomena. Which makes it like a very interesting avenue to try to find a double copy for this system. And in particular, trying to find perhaps something like a classical double copy for the field that we've chosen, sort of analogous to the Cartiel double copy. Right, that's me.
Thank you for the great talk. So in regards to like the relationship to like Hawking radiation, because normally in Hawking radiation, like with the particle that stays in and gets sort of back hole, you have like problems with entropy, right? It goes from a pure state to a mixed state. Do you think you'd expect to see something like that with this sort of electrons in the background field, or do you think just the way it's constructed, it's will be like that? Kind of
Well, I don't know. Anton?
I think it's very hard to see because all the electron degrees of freedom basically just kind of vanish.
yeah, because it's inside just like massive.
Yeah,
Like,
they really are gone from the theory.
you think if you put like some sort of like more conditions on that external field, maybe see something else, maybe because it's so I'm assuming you just put like does a kind of like almost like a physical like strong field in some sense. Maybe if you put like
It's not that which is doing it. I think there are to see what you want to see. I think what you should do is approach this probably like the 2-time formalism that people have used before. So there's no problems with the unitarity or anything like that. Everything's perfectly well defined. It's an absolute. No one wants to do stuff with 2-time, but then you do have like the complete Hilbert space is still there. You can do all this kind of stuff.
okay.
Maybe a quick question, like, so you do expect the wave function of Schwarzschild to have a discontinuity at the horizon, like with the term proportional to the temperature of the black hole, I think. So that should be similar to your electric field, like exponent in some sense.
Yeah, I mean, we've been trying to sort of find a way to associate sort of a temperature with this horizon, but nothing conclusive yet.
Is it possible that from some sort of on-cell conditions, you would need this B plus on the denominator to be always greater minimum B such that you never hit the ball?
So say that again?
So you have this ball on the wave function.
Yeah.
Would it be that from on-cell considerations, this ball is never reached? Because you're scattering, therefore you're above whatever threshold it needs to be free, right? Otherwise it would be bound and not scattering.
Yeah, I mean, classically it never reaches that point. Yeah, you're right. I mean, but for the wave functions, we should be able to. I mean, it should be a solution to to the Klein-Gordon equation everywhere. So we need to reach that pole somehow.
In a way, the on-shell condition is the problem. So it tells you that P plus is positive. And it just decreases and it decreases and it decreases as you go through the field. So you do hit the pole. Well, one species of particle. It's electrodynamics, not the other species.
Are you also considering doing a similar approach to different types of electric fields? Because, for example, if you're looking for a classical double copy of that background field, I don't know, that doesn't seem like a particularly likely one to me naively, but maybe if you tried it with some other electric fields, it would work better.
Yeah, I mean, the point of this electric field or this class of electric fields is that it's easy to study analytically. Whereas if you have sort of time-dependent field, it's a lot more difficult. So sort of not the nice part about this.
Yeah, of course,
You
yeah.
always run into some problem.